Hello, my name is Alan Doucette, and I'm speaking to you from Dalhousie University in Halifax, Nova Scotia. And I'm here to talk to you today about our separation platform, which we term gel-free, and it's a device that separates proteins according to their molecular weight with recovery in the solution phase. So let's begin this story talking about intact protein separation. And traditionally, this has been a gel-based world. So what you're looking at here is a classical two-dimensional gel electrophoresis separation, and it works on the principle of combining two independent methods of separation, first by protein's isoelectric point, followed by protein separation according to molecular weight. And this is an absolutely beautiful separation. Each of these spots would represent one or maybe a couple of individual proteins, and we see over 1,000 spots here. But of course, the story isn't done, because if we're interested in knowing what that protein is, then we'd usually use mass spectrometry and digest these proteins. So you take razor blades and cut the spot out, and most of us are familiar with this type of technology. Now, if we want to do protein separation in the solution phase, we have a few options available to us. So it's basically exploiting the differences in the properties between the proteins themselves. And when you think about it, there really aren't too many different categories to work with. So we could deal with protein affinity, so that's essentially protein A binding to protein or moiety B. So think about antibody enrichment or protein depletion. You can also use this to apply PTM pull down, so things like phosphoprotein enrichment or glycoprotein enrichment. There's polarity or protein hydrophobicity, so reverse phase chromatography is the perfect example of that. There's also protein separation by charge or their isoelectric point, and usually we think of ion exchange and solution IEF, so that's the isoelectric focusing as described in the 2D gel, which can also be applied in the solution phase. And then finally, we can take advantage of the size of the protein molecule, so gel permeation chromatography or things like centrifugation, and of course this new technology which we're terming gel-free. Now, just to sort of let you in on things, our group isn't only interested in the size-based separation, so we do work on the other techniques. So here's an example of some reverse phase separation, taking advantage of some different solvent systems to separate proteins, and a custom-designed isoelectric focusing platform, providing us with 8 channels of protein separation. So here's the device, the gel-eluted liquid fraction entrapment electrophoresis platform. This is the original design that we came up with, and it's a single-channel platform. And to describe how it works, it's everything that you know about SDS-PAGE can be applied to gel-free. Really, the only difference here is that the proteins, well, they're first separated within a gel. The gel is cast inside of a tube. And in terms of dimensions, here we're looking at a 6 millimeter internal diameter gel column. But as they traverse the tube, the small proteins will move through quicker as they see through the acrylamide pores. But if we keep applying this voltage, then eventually the proteins will fall off the edge of the tube. So the tube stops at this point right here, where they're trapped in this little pocket. So you can see a little hole in there, and essentially we've got a dialysis membrane placed at the back of that, and we can grab fractions in the liquid phase. So why call it gel-free? Well, if you think about it, proteins start in solution, they finish in solution, and therefore they're freed from the gel once they complete the separation. So you can kind of think of this as a form of liquid chromatography, although it's a different type of pump. Now, the concept here of doing continuous elution electrophoresis is certainly not new. It's been around for a number of years, and there are commercial technologies that take advantage of this type of separation. So you're looking at the PrEP cell, which is designed for protein purification. The way that the PrEP cell works is quite different, and it really comes down to the method of protein trapping once they elute from the gel column. So I already described our collection chamber, and you can see the end of the gel right here. So the collection chamber is this pocket, and you see a dialysis membrane placed just behind that collection chamber. So once the proteins are migrating through the gel and they leave the gel column, they'll stay trapped in this little pocket, and that hole at the top is just to allow a pipette tip to grab in and reach fractions according to time, and the later we go during separation, the larger the proteins get. So this is how the prep cell performs, and I grabbed one of these slides from some work that was published by Neil Kelleher. And you can see that as time progresses and we go to larger fraction number, the size of the proteins will increase. And this represents a 6-hour separation. Each of the fractions are approximately 15 mils in volume. And there is sort of an upper mass limit because proteins progressively take longer to elute from the column. So this is the performance of the gel-free system. And you can see that there's quite a number of differences. And first of all, if you consider the molecular weight range, this is approximately what's represented from the prep cell design. So we're extending to a much larger molecular weight range. In particular, we're also covering the low mass as well as the high mass limit. Approximately 10 kilodalton to 150 kilodalton range is shown here. The fractions themselves are much smaller volume, on the order of 100 microliters per fraction, and the time of this separation is much quicker as well. So this represents a 90-minute separation. Now, how do we get that to go so quickly? And really, it comes down to the gel column itself. We use extremely short gel columns, 1 centimeter long, and you can see this is the exact same gel that I've shown in the previous slide. You can see that we're getting good resolution between each of these fractions. Now, you might say, well, why not try a longer column? Well, if you do use a longer column, then, well, first of all, it would take longer for the separation to be completed. So 3 times the column length is approximately 3 times the separation time. But in terms of resolution, things really haven't gotten that much better. So if going to a longer column achieves essentially the same degree of separation, but only taking longer, then we might as well stick with the short one. And the reason to explain that, it's really coming down to broadening as the separation takes place.